Hello, welcome to the ninth module of the Python Fundamentals course, where we'll cover reading and writing data from text and binary files and discover how to manage resources such as files elegantly using context managers. To open a file in Python, we call the built-in open function. This takes a number of arguments, but the most commonly used are file, the path to the file, this is required, mode, which specifies read, write, append, and binary or text mode. This is optional, but we always recommend specifying it for clarity. Explicit is better than implicit. Encoding. If the file contains encoded text data, this is the text encoding to use. It's often a good idea to specify this. If you don't specify it, Python will choose a default encoding for you, which may not be what you want. At the file system level, files contain only a series of bytes. Python distinguishes between files opened in binary and text modes, even when the underlying operating system doesn't. Files opened in binary mode return and manipulate their contents as bytes objects without any decoding. Binary mode files reflect the raw data in the file. A file opened in text mode treats its contents as if it contains text strings of the str type, the raw bytes having first been decoded using a platform-dependent encoding or using the specified encoding if given. By default, text mode also engages support for Python's universal newlines. This causes translation between a single portable newline character in our program strings, \n, and a platform-dependent newline representation in the raw bytes stored in the file system, for example carriage return newline, \r\n, on Windows. Getting the encoding right is crucial for correctly interpreting the contents of a text file, which is why we labour the point. If you don't specify an encoding, Python will use the default from sys.getDefaultEncoding. In our case, that is UTF-8, but there's no guarantee that the default encoding on your system is the same as the default encoding on another system with which you wish to exchange files. Better for all concerned to make a conscious decision about the text to bytes encoding. You can get a list of supported text encodings in the Python documentation. Let's start by writing some text to a file. We'll be explicit about using the UTF-8 encoding because we have no way of knowing what your default encoding is. We'll use keyword arguments to make things clearer still. The first argument is the file name, wasteland.txt. The mode argument is a string containing letters with different meanings. In this case, W means write and T means text. All mode strings should consist of a read, write, or append mode. One of R, W, or A with the optional plus modifier should be combined with a selector for text or binary mode, T or B. So typical mode strings might be WB, write binary, or AT, append text. Although both parts of the mode code support defaults, we recommend being explicit for the sake of readability. The exact type of the object returned by open depends on how the file was opened, dynamic typing in action, but for our purposes it's sufficient to know that the object returned is a file-like object, and as such we can expect it to support certain attributes and methods. We've shown previously how we can request help for modules and methods and types, but in fact we can request help on instances too. This makes sense when you remember that everything is an object. Browsing through the help, we can see that F supports a method write. Quit the help with Q and continue at the REPL. The write call returns the number of code points or characters written to the file. Let's write a few more lines. It is the caller's responsibility to provide new line characters where they are needed. There is no write line method. When we've finished writing, we should remember to close the file by calling the close method, f.close. Note that when we close the file, all the contents become visible. Closing files is important. If you now exit the REPL and look in your file system on Unix with ls-l, you should see the wasteland.txt file with 78 bytes. On Windows with dir, you should see wasteland.txt with 79 bytes. This is because Python's universal new line behavior for files has translated the line endings to your system's native endings. The difference is because Python's universal new line behavior for files has translated the line endings to your platform's native endings. The number returned by the write method is the number of code points or characters in the string passed to write, not the number of bytes written to the file after encoding and universal new line translation. In general, when working with text files, you cannot sum the quantities returned by write to determine the length of the file in bytes. To read the file back, we use open again, but pass a different mode string, in this case RT for read text. If we know how many bytes to read, or if we want to read the whole file, we can use the read function. Looking back through our REPL, we can see that the first write was 32 characters long. We can read that back with a call to the read method. In text mode, the read method accepts the number of characters to read from the file, not the number of bytes. The call returns the text and advances the file pointer to the end of what was read. The return type is str because we opened the file in text mode. To read all the remaining data in the file, we can call read without an argument. This gives us parts of 2 lines in one string. Note the new line character in the middle. At the end of the file, further calls to read return an empty string. Normally, when we are finished reading a file, we would close it, but for the purposes of this exercise, we'll keep the file open and move the file pointer back to the beginning of the file using the seek method, with a 0 offset from the start of the file. The return value is the new file pointer position. Using read for text is quite awkward, and thankfully Python provides us with better tools for reading text files line by line. First of these is the readLine function. The returned lines are terminated by a single new line character if there is one present in the file. The last line here does not terminate with a new line because there is no new line sequence at the end of the file. You shouldn't rely on the string returned by readLine being terminated by a new line. Again, the universal new line support will have translated to \n from whatever the platform native new line sequence is. Once we reach the end of the file, further calls to readLine return an empty string. Let's rewind again with seek. Sometimes when we know we want to read every line in the file and we're sure we have enough memory, we can read all lines into a list with the readLines method. This is particularly useful if parsing the file involves hopping backwards and forwards between lines. It's much easier to do this with a list than with a file stream of characters. This time we'll close the file before moving on with g.close. Sometimes we would like to append to an existing file. We can do that by opening the file with mode A, which opens the file for writing, appending to the end of the file if it already exists. In this example, we combine that with T to be explicit about using text mode. Although there is no writeLine method in Python, there is a writeLines method, which writes an iterable series of strings to a stream. If you want line endings on your strings, you must provide them yourself. This seems odd at first, but it preserves symmetry with readLines, whilst also giving us the flexibility for using writelines to write any iterable series of strings to a file. Notice that only 3 lines are completed in this example. I say completed because the file we're appending to doesn't end with a new line. The culmination of these increasingly sophisticated text file reading tools is the fact that file objects support the iterator protocol, with each iteration yielding the next line in the file. This means they can be used in for loops and any other place where an iterator can be used. At this point, we'll take the opportunity to create a Python module, files.py. We'll use this to contain the code for the following example. When run, this program opens the file name passed as its command line argument and iterates over the file with a for loop line by line, printing each line as it goes. Let's run this program directly from the system command line, passing the name of our text file wasteland.txt. The double line spacing occurs because each line of the poem is terminated by a new line and then print adds its own. To fix that, we could use the strip method to remove the white space from the end of each line prior to printing. Instead, we'll use the write method of the standard out stream. This is exactly the same write method used to write to the file. Files and streams are closely related and can be used because the stream is a file-like object. We can get hold of a reference to the standard out stream from the sys module. Rerunning, we now get single-space text. Now, alas, it's time to move on from one of the most important poems of the 20th century and get to grips with context managers. For the next demonstration, we're going to need a data file containing some numbers. We'll write a sequence of numbers called recommend sequence to a text file, with one number per line. Recommend sequence itself isn't important to this exercise, we just need a way of generating numeric data, so we won't be explaining the sequence generator. Feel free to experiment though. The module contains a generator for yielding the recommend numbers and a function which writes the start of the sequence to a file using the writelines method. A generator expression is used to convert each number to a string and add a new line. itertools islice is used to truncate the otherwise infinite sequence. We'll write the first 1000 recommend numbers to a file by executing the module, passing the file name and series length as command line arguments. Now let's make a complementary module, series.py, which reads this data file back in. This simply uses a for loop to iterate over the file, reading one line at a time, and strips the new line with a call to the strip string method, and converts it to an integer. Running it from the command line, everything works as expected. Now let's deliberately create an exceptional situation. Open recommend.dat in a text editor and replace one of the numbers with something that isn't a stringified integer. Save the data file and rerun series.py. The int constructor raises a value error which is unhandled, so the program terminates with a stack trace. One problem here is that our f.close call was never executed. To fix that, we can insert a try finally block. Now the file will always be closed. Doing so opens up the opportunity for another refactoring. We can replace the for loop with a list comprehension and return the list directly. Even in this situation, close will be called. The finally block is called, however the try block is exited.
Beautiful is better than ugly. Sugary syntax, fewer defects attained through sweet fidelity. The with block syntax is so-called syntactic sugar for a much more complex arrangement of try except and try finally blocks. Few of us would want our code to look this convoluted, but for it to be reliable, this is how it would need to look without the with statement. Sugar may not be good for your health, but it can be very healthy for your code.
Up to now, our examples have all followed a pattern. Open a file, work with the file, and close the file. The close is important because it informs the underlying operating system that you're done working with the file. If you don't close a file when you're done with it, it's possible to lose data. There may be pending writes buffered up which might not get written completely. Furthermore, if you're opening lots of files, your system may run out of resources. Since we always want to pair every open with a close, we want a mechanism that enforces that and makes sure it happens even if we forget. This need for resource cleanup is common enough that Python implements a specific control flow structure called with blocks to support it. With blocks can be used with any object which supports the context manager protocol, and that includes the file objects returned by open. Exploiting the context manager nature of the file object and using a with block, our read series function can become very simple. We no longer need to call close explicitly because the with construct will call it for us when, and by whatever means, execution exits the block. Now we can go back and modify our recommend series writing program to use a with block too. This also removes the need for an explicit close. To demonstrate handling of binary files, we need an interesting binary data format. The BMP file format contains device-independent bitmaps and is simple enough that we can make a BMP file writer from scratch in this session. The code will be placed in a module bmp.py and is straightforward from a file handling point of view. For simplicity's sake, we have decided to deal with 8-bit grayscale images, which have the nice property that they are 1 byte per pixel. The write grayscale function accepts 2 arguments, the file name and a collection of pixels. As the docstring points out, this collection should be a sequence of iterable series of integers. A list of lists of int objects will do just fine. Each int is a pixel value from 0 to 255. Each inner list is a row of pixels from left to right, and the outer list is a list of pixel rows from top to bottom. The first thing we do is figure out the size of the image by counting the number of rows to give the height and number of items in the 0th row to get the width. We assume, but don't check, that all rows have the same length. In production code, that's a check we would want to make. Next, we open the file for write in binary mode using the WB mode string. We don't specify an encoding. That makes no sense for raw binary files. Inside the with block, we start writing what is called the BMP header, which begins the BMP format. The header must start with a so-called magic byte sequence, BM, to identify it as a BMP file. We use the write method, and because the file was opened in binary mode, we must pass a bytes object. The next 4 bytes should hold a 32-bit integer containing the file size, but we don't know that yet. We could have computed it in advance, but we'll take a different approach of writing a placeholder value for now, then returning to this point later to fill in the details. To be able to come back to this point, we use the tell method of the file object to give us the offset from the beginning of the file for the file pointer. We'll store this in a variable which will act as a sort of bookmark. We write 4 0 bytes as a placeholder, using escaping syntax to specify the zeros. The next 2 pairs of bytes are unused in this format, so we'll just write 0 bytes for them too. The next 4 bytes are for another 32-bit integer which should contain the offset in bytes from the beginning of the file to the start of the pixel data. We don't know that value yet either, so we'll store another bookmark using tell and write another 4 bytes placeholder. We'll return here shortly when we know more. The next section is called the image header. The first thing we have to do is write the length of the image header as a 32-bit integer. In our case, the header will always be 40 bytes long. We'll just hardwire that in hexadecimal. Notice that the BMP format is little endian. The least significant byte is written first. The next 4 bytes are the image width as a little endian 32-bit integer. We call a module scope implementation detail function here called _int32 to bytes, which converts an int object into a bytes object containing exactly 4 bytes. We then use the same function again to deal with the image height. The remainder of the header is essentially fixed for 8-bit grayscale images, and the details aren't important here, except to note that the whole header does in fact total 40 bytes. Each pixel in an 8-bit BMP image is an index into a color table with 256 entries. Each entry is a 4-byte blue, green, red color. For grayscale images, we need to write 256 4-byte gray values on a linear scale. This snippet is fertile ground for experimentation, and a natural enhancement to this function would be to be able to supply this palette separately as an argument to the function. At last, we are ready to write the pixel data, but before we do, we make a note of the current file pointer offset using tell, as this is one of the locations we need to go back and fill in. Writing the pixel data is straightforward enough. We use the reversed built-in function to flip the order of the rows. BMP images are written bottom to top. For each row, we simply pass the iterable series of integers to the bytes constructor. If any of the integers are out of the range 0 to 255, the constructor will raise a value error. Each row of pixel data in a BMP file must be a multiple of 4 bytes long, irrespective of the image width. To achieve this, we compute the number of padding bytes required by subtracting the row length modulus 4 from 4. This value is used with the repetition operator applied to a single 0 byte to produce a bytes object containing 0, 1, 2, or 3 bytes. We write this to the file to terminate each row. After the pixel data, we are at the end of the file. We undertook to record this offset value earlier, so we record the position using tel into an end-of-file bookmark variable. Now we can rewind and fulfill our promises by replacing the placeholder offsets we recorded with the real thing. To do this, we seek back to the size bookmark we remembered back near the beginning of the file and write the size stored in the EOF bookmark as a little endian 32-bit integer using our _int32 to bytes function. Finally, we seek to the pixel data offset placeholder bookmarked by pixel offset bookmark and write the 32-bit integer stored in pixel data bookmark. As we exit the with block, we can rest assured that the context manager will close the file and commit any buffered writes to the file system. We're not going to write a full-blown BMP reader, although that would be an interesting exercise. We'll just make a simple function to determine the image dimension in pixels from a BMP file. We'll add the code into bmp.py. Of course, we use a with statement to manage the file, so we don't have to worry about it being properly closed. Inside the with block, we perform a simple validation check by looking at the first 2 magic bytes that we expect in a BMP file. If they're not present, we raise a value error, which will of course cause the context manager to close the file. Looking back at our BMP writer, we can determine that the image dimensions are stored exactly 18 bytes from the beginning of the file. We seek to that location and use the read method to read 2 chunks of 4 bytes each for the 2 32-bit integers which represent the dimensions. Because we opened the file in binary mode, read returns a bytes object. We pass each of these 2 bytes object to another implementation detail method _bytes to int32, which assembles them back into an integer. The 2 integers representing image width and height are returned as a tuple. The _bytes to int32 function uses bitwise left shift and bitwise OR, which is the vertical bar or the pipe symbol, together with indexing of the bytes object to reassemble the integer. Notice that indexing into a bytes object returns an integer. Let's try our new BMP dimensions function on the mandel.bmp file. There's a notion in Python of file-like objects. This isn't as formal as a specific protocol, like sequence protocol is for tuple objects, but thanks to the polymorphism afforded by duck typing, it works well in practice. This is where the easier to ask forgiveness than permission philosophy comes into its own. If you want to perform seek on a file-like object without knowing in advance that it supports random access, go ahead and try, literally, but be prepared to fail if the seek method doesn't exist, or does exist but doesn't behave as you expect. You might say, if it looks like a file and reads like a file, then it is a file. We've actually seen this already. The objects returned to us when we open files in text and binary mode are actually of different types, although both with definite file-like behavior. We saw one of them in action back at the beginning of the course used to retrieve data from a URL on the internet. Let's exploit this polymorphism across file-like objects by writing a function to count the number of words per line in a file and return that information as a list. Now we'll open a regular text file containing the fragment of T.S. Eliot's masterpiece we created earlier and pass it to our new function. The actual type of real file is _IO text IO wrapper, which is an internal Python implementation detail. We'll now do the same using a file-like object representing a web resource referred to by a URL. In this example, the type of web file is http.client.http-response, a quite different thing. However, since they are both file-like objects, our function can work with both. There's nothing magical about file-like objects, it's just a convenient and fairly informal description for a set of expectations we can place on an object which are exploited through duck typing. The with statement construct can be used with any type of object which implements the context manager protocol. We're not going to show you how to implement that in this course, but we will show you a simple way to make your own classes usable with the context manager using the code in fridge.py. The module includes a class, Refrigerator Raider, which, well, raids a refrigerator. It has three methods: open, which opens the fridge door; take, which gets some food from the refrigerator; and close, which closes the fridge door. There's also a module scope driver function, raid, which performs a full raid on the refrigerator. We'll import raid into the REPL and go on the rampage. First, let's take some bacon. As expected, the code opens the fridge doors, finds the bacon, takes the bacon, and closes the fridge door. Very responsible. It's important that we remember to close the door, so the food will be preserved until our next raid. Now let's try another raid for deep fried pizza. This time we were interrupted by the health warning and didn't get around to closing the door. We can fix that by using a function called closing in the Python standard library context_lib module. After importing the function, we wrap our call to the refrigerator raider constructor in a call to the closing function, which wraps our object in a context manager that always calls the close method on the wrapped object before exiting. We use this object to initialize the with block. Now when we execute a raid, the fridge door is closed twice. We see that our explicit call to close is unnecessary, so let's fix that up too. A more sophisticated implementation might check that the door was already closed and ignore subsequent requests. Let's try again. This time, even though the health warning was triggered, the door was still closed for us afterwards by the context manager.